the brain is full of cabling. Is extremely like most of the mass of the brain is what we call white matter. It's the cabling, and so imagine all these highways of information are crossing. If there is a tumor there, the neurosurgeon may accidentally cut a pathway that allows you to speak. We know from neuroscience that, from research in neuroscience, that pretty much all brain disorders, for example, they have a neurological effect. You see the pathways in the brain changing, you see change, you see physiological change. And most of the companies, what they do, as you know, they have small engineering teams and a massive sales team or marketing team. And they just want to scale things. They want to get something ready and scale it. But this is not how scientific open source works. Scientific open source, not only DiPi, but many other projects, they are focusing on long term, much longer term. And often we are being attacked for that.
Welcome back to our episode of Two Poles Apart. We're having a wonderful guest today with a wonderful story. Aleph, we're going to talk a little bit more now. We've talked about your career and some of the decisions and how the world sometimes aligns to get us where we are. But if you don't mind, I'd love to focus a little bit more on the actual field of study, work that you do. There's a specific product you are working on, and could you tell us a bit more about it?
Yes, of course. The biggest project we are working on, and we have been working on this now for close to 20 years. It's a non-stop effort. It's called DiPi, D-I-P-Y. And that is a software project. It's a software library for analyzing and processing diffusion MRI data. Diffusion MRI data are data sets that you can get from any MRI, any magnetic resonance imaging scanner, from any MRI machine can generate these data sets. And with these data sets, you can actually see and study brain connectivity. You can also understand the underlying anatomy without opening the body, without surgery, in vivo, directly, in a non-invasive way. And you can figure out all sorts of things about the underlying distributions. Maybe there is edema, maybe there is disease. And it's not only about the brain. You can study the brain, the heart, muscles, all sorts of organs can be studied with diffusion MRI. The problem you have in diffusion MRI is that it is a four-dimensional sequence data set. It's four-dimensional, and it's a very advanced technique. It's very mathy. It needs a lot of machine learning optimization. It has many stages of pre-processing. So as the data are coming out from the scanner, we take this data and then we have to run 30 to 100 algorithms until we give the data to the doctor, so the doctor can use them or other researchers can use the results in a meaningful way. Otherwise, they cannot use them. And this requires the development of software, scientific software. And the problem you need to solve there, they're very hard. They are at the limit of what humanity can solve right now. And we are developing those algorithms and those methods ourselves. But also, we're doing that in a community-driven open source fashion. So DiPi is that software project, that international software project, where people who have ideas and contributions where scientists, engineers, computer scientists, also cognitive scientists have ideas. They can share these ideas in the same code base to solve the hardest of this problem. So we have now more than 40 universities involved. We have more than 200 contributors. There is I don't even remember how many countries are involved. And this is something that was set, that international concept was set from day one. When I started DIPI back in 2008, immediately I invited people from other labs, from some of them were from South Africa, some of them were from USA, from Berkeley, for example, or from UCSF. Invited people across the globe to share their ideas in the same place. And the reason is because it's unlikely a single lab will solve all the processing problems that the field requires. But when the field was still new, people thought that 1-2 labs can do it. And this was an intuition there where I came in and said, this is not an easy problem. You're claiming this problem is easy, but this is not, it's actually requiring international effort. It's a small Manhattan project in a sense. It requires international effort. And it has to be open if you want to really truly help the patient, really truly help the doctor. It has to be open. The people can go and see the algorithms, see the methods, understand, learn how to use them. This is a very important aspect.
So it's like an international startup, I guess, with again a very a noble objective, I guess, as well. When everyone gets together and basically develop methods of, getting a very, I guess, data heavy issues or problems and translating it into something that can help. Is that a well? Did I understand it correctly, Aleph, or am I simplifying it too much?
Yes, it is correct. It is an effort to, like, the mission statement of DIPY, of DIPI, is make it easy to do diffusion MRI research. However, to make it easy to enable the researchers, enable the clinicians, we have to invent a lot of methods from the bottom up. And it's not that you can go and take something that it was made for computer vision or for general AI and you can just use that and it just works. That you can do in some medical imaging cases, but not in diffusion MRI.
Okay. So what you were saying with this four-dimensional thing, so it's of course the three kind of dimensions of the world plus time. Yes, that's the four-dimensional.
The fourth dimension is not time, is it's a gradient. This is a bit technical.
I see.
It's a change in the magnetic gradient in the scanner.
Okay.
So as we're scanning the subjects, the participants, as the time, as we say, passes, we change the magnetic gradient. And by changing the magnetic gradient, we're doing some kind of tomography for its position in space.
Okay.
And that allows us to recover an entire distribution for its position in space for the tissue we are modeling. Is it the brain? Is it the muscle? Is it heart?
Yeah, so in a sense, it's kind of funny, like I work with data. In my field, I work with data, but in order, let's say, for me to actually say something from such studies, you need the whole processing of DIPI to get to the numbers that mean something actually either for medical research or for medical decisions. So it's not like blood pressure that you put the cuff on and basically what you see is what you get. And I mean, development of even measuring blood pressure, that took some time. But this is much, much simpler, yes? It's based on basic physical principles. And, now nobody thinks twice about measuring blood pressure. With such technologies, like with MRI technology by itself, it's already a huge breakthrough. But what we can do with MRI, that's why this multidisciplinary work is needed, yes? There are not only algorithms, but also, as you were saying, well, we can just throw the computer vision algorithm into it, but it's not exactly. We need to think about it a bit. And you put it all in this kind of ecosystem where you start with the data that you collect from the scanner. And at the end of the day, you can say, well, now we know, let's say, why Parkinson's disease, why people with Parkinson's disease are different. Like what changed in the connectivity in the brain, yes?
Yes. The pathways in the brain changing, you see change, you see physiological change. And diffusion MRI is sensitive to that. And we can see those changes. And I have good news now. In 2026, there's some incredible things happening. You can combine diffusion imaging, diffusion MRI, and ultrasound, and do non-invasive surgery. So basically, you have a patient. The patient gets in the MRI scanner. Let's say there is a disease, for example. Let's say there is a very serious disease like Parkinson's, some diseases that create tremors, creates movement disability. We can now create a system, have a system, an ultrasound system around the head of the patient that targets sound while the patient is in the MRI scanner. And by targeting sound, you can now go and hit some regions and dissolve, imagine something like edema, tumor, and you can do it directly on the pathways, on the information pathways of the brain. And this is amazing. You don't need to do actual surgery, and you don't need radiation as well.
So it's much safer as well.
It's much safer. It's much easier. It's easier for the body to adapt to it. At the same time, of course, there is still need of surgery. Neurosurgery is very important. And what software like DiaPi provides to the neurosurgeons is it provides them a map. It helps them with planning. So imagine you have a brain and there is a tumor in the brain. The brain is full of cabling. It's extremely like most of the mass of the brain is what we call white matter. It's the cabling. Those are the information pathways. Most of the volume of the brain has those. And they're very packed together, they're very tied together. And it's not the only tied, the human brain has also crossing pathways. The pathways are crossing. And so imagine all these highways of information are crossing. And if there is a tumor there, the neurosurgeon may accidentally cut a pathway that allows you to speak, allows you to think, allows you to move. So, because from the moment you cut a pathway, it's like, for example, there is a pathway called arcuate fasciculus. It's a language pathway. If there is a cut in that pathway, you will be thinking about speaking, but nothing will come out of your mouth. Nothing. just there's no way, there's no connection anymore. There's no the link is broken, let's say. So the neurosurgeons, they use these maps. They can use these maps to then replan, change their surgical direction, decide a different path to go and how to remove the tumor and how to do it in a cleaner way. And there are the aggressive tumors, of course, that they need immediate surgery, but there are also benign tumors in the brain that they go and they press on different nerves and they create all sorts of issues there. And we're trying to build the technology to disentangle what is disease than what is healthy and preserve the healthy part.
Okay.
Yes.
So this is one of the applications.
One of the applications.
Sorry if I may ask.
When I hear about the way how you describe, and I know it's massively complicated process, I guess, or the highways you've talked about and the crossing of it. So I'm guessing you've mentioned that the technology can help us to understand how something is built or wired without, actually have to physically going into it. So, I mean, going with this path, and correct me if I'm wrong, but I live in a world that I think like we still don't understand our brain completely. Is that true, or are we? So
it is true.
Is
yes.
that is that the way to start to actually get to a point to really understand, how our body or how the brain works? Because the way you describe it's almost starts to the wires or the way you're creating a map. Actually, in my mind, starts to go into we start to understand it on a different level or at thing. Is that the direction of travel for this, or am I completely wrong?
No, you're not wrong. To really understand the brain it's a problem. I wish I could say that diffusion MRI can solve all that, but you need many modalities. You need to combine many different modalities: diffusion MRI, functional MRI. We said ultrasound. There is a series of things. You need also biochemical studies. You need to also study hormones. You need to study. You hear a lot about dopamine and epinephrine, and so it's a multi-scale thing. And still, the point, like let's say you have understand the neurology completely, and there are people who study if the individual neurons, even how they work. We are studying more systems of neurons.
And their systems. This is not like 5 neurons or 10 neurons.
Yes, this is not.
This is usually thousands, or tens of thousands working together.
Yes. But the brain has trillions of connections. So
yes.
So it's a wire, but there is some scale limitation. So to really understand how the brain works, you have to multi-scale. You have to have that requires the entire field of neuroscience and the medical field. And it's not only the brain; it's also the body. Then the brain is connected with the spinal cord. All the nerves, most of the nerves coming out of the spinal cord. That's another part of the nervous system. And even if you understand the entire neurology of it and the entire physiology of it, then what creates a mind? What creates a thinking? And then what is the conscious part of it? And what is the unconscious part of it? Some of the things we can see, for example, like with other modalities, with functional MRI, we can see, for example, what areas of the brain require a lot of oxygen when you're doing particular tasks. There are models that have been created about that. There are models that they think, where could be like the switch? Where are the switches where suddenly you become conscious? Let's say you sleep and you wake up. What changed in the brain?
What changes?
What changed? What changed? Where did it change? Those are the great questions and challenges. Let me also tell you something else. Diffusion MRI itself has one challenge which is for sure at the limit of our ability, of our engineering and computational ability right now. It's called what is the name? The combinatorial problem of tractography. When you get the signal from the data from the MRI scanner, there are some assumptions even in that signal. There are some limitations in that signal themselves, which we need to go beyond. Those limitations, they create some combinatorial problems that are very hard to solve. And I think this is maybe we will see it in the next 5-10 years. If we can solve that combinatorial problem of tractography, it would be, again, an international effort. And it would be a really great outcome. Basically, what you get if you solve this problem is you end up having such an accurate reconstruction of the pathways of the brain, which would be like opening the brain and looking at slice by slice. You could have like a perfect match.
Is it more of a computational problem? Because you said combinatorial.
It's a combinatorial problem that arises from limitations of the physical signal of the MRI signal. There are some symmetries and there are some limitations of what you can know about the tissue you are studying, and there are some limitations coming from even the photons you're measuring from the scanner. There are some limitations also on so there is a combination of measurement limitations.
Okay. So is it also a technological problem? So for example, higher field strength, like 70 scanners, would that help with that or no? Or it's more on the processing side? I'm just trying to understand, maybe I'm going too deep into that, but is it the physical problem, technological problem, or computational?
Altogether.
Okay.
Everything.
Altogether.
Okay.
So there is the problem of measurement, that we can say physical. There is the problem of another technological is the scanner has some limitations. Well, basically, there is something called gradient switching. You change the gradients in the magnetic gradients. If you start changing them too much, it starts becoming dangerous for the patient. So that creates another issue there. So you have to reduce that. Then the signal comes with some symmetries which you don't want to actually do better pathway tracking. It would be better to have all the asymmetries known, but it comes with symmetries. Those symmetries create some issues there. I'm just giving you some examples. And then there is the technology to build we don't have the algorithms right now. We have some algorithms, but we need algorithms that can acquire, because the information is not in the signal fully, we need to acquire information from neuroanatomists and integrate it. And that requires prior. How do you integrate that prior? And at the same time, deploy a tool, a software, and working with all the data that's available. So there are different levels there. But
so in a sense, you're saying you will not lose your job for a few more years because there's always more to do. And
I would definitely not lose my job. Even this problem is solved, I will switch to another, imaging, or I'll move to sound.
That's the best approach. That's the spirit. Yeah. And Aleph, when you talk about when coming back to the product, to DiPi and the library of, I guess, people working together to trying to, I guess, interpret or make something very complicated usable on the everyday life. It just reminds me or a question sparks in my mind around, is that something or a product like that could work for other fields? And what I mean by that is like, I don't know, we have other complex problems that we have where I guess data is limited. There's a lot of elements when it comes to, I don't know, I'll go world hunger, or maybe, just a very specific problem in a specific part of the world or whatever. Do you think, creating of finding patterns or the ways of translating certain elements, which might be economical, which might be, I don't know, from sociology or other patterns, would also follow the same pattern, or am I taking it a bit too far over here?
No, you're not taking it far. Actually, this is an amazing question, and I haven't seen this question being asked anywhere else. This is a very important question. So DaiPy is an open source software with a permissive license, allows everyone to use it and create products out of it and do research, do anything they want. We're not going policing people how to use our technology. And we have a clear mission, as we discussed, and we are working online with other researchers, scientists, professors, all sorts of different fields to get this job done. So there is this, team effort that is asynchronous, and it's purposeful. There is a need. We build something because there is a need. It's not that there is no need and we're just building it for our fun. I hear a lot of people claiming that the open source developers are just doing what they like for fun, for the fun of it. I think people tend to generalize, and it is scientific software. It's scientific engineering software. It is it's solving scientific problems, and I think this is a very important point. So there are more than 30 startups using DaiPy. They built. If DaiPy didn't exist, these startups will have very, very hard time starting and surviving. Also, the big industry, some of the big pharmaceuticals use, some of the big MRI device manufacturers, they're using DaiPy. And it's interesting why they didn't make something like DaiPy themselves. Why that should be an academic project. The reason is because it's hard. It requires a lot of thinking. It requires a lot of innovation. And most of the companies, what they do, as you know, they have small engineering teams and a massive sales team or marketing team. And they just want to scale things. They want to get something ready and scale it. But this is not how scientific open source works. Scientific open source, not only DaiPy, but many other projects, they are focusing on long-term, much longer term. And often we are being attacked for that, because the code that gets in our code bases has to be tested, it has to be reviewed carefully. So it takes time to build something like DaiPy. For example, now it took us pretty much 20 years to do it, but it was always useful, but it was never as useful as it is now. It took time to build all the necessary foundations. So what happens these days is that people are trying to find cheap solutions for everything, like cheap solutions. Just get the money, get everything quickly. Just go present this work or do this other thing or get the deal. It's everything about that. Like scale as quickly as you can, get the job as quickly as you can, and that is on the opposite side of what we are doing. We are trying to build something that works well. It works in all platforms, in Windows, in Mac, in Linux. It will work on the cloud. It will work extremely well. It's going to be fast, right? You don't want the surgeon be waiting on some computational software. You want to have results quickly. And the people who have got involved in such projects, they did extremely well career-wise. Even though they did the long term, they look at, let's do something beneficial. they all did very well. They went to Google and to Microsoft Research and to, build their own labs. So they all did very well because they actually developed a skill.
Yep. Yep.
I would say multiple skills. Because in open source, we do the development, we do also the sales, we do also the marketing, we do everything ourselves. So you learn to understand all sorts of things. But it's led by the engineers. The engineers are leading that. And if you think about this, you will see that a lot of companies use that model into an industrial setting. Unfortunately, the companies, they have benefit extremely from open source. So if tomorrow I just take all the open source projects and I just say finished, I introduce a bug and I say finished, there is no open source anymore, you will see all the giants collapsing. You will see it will take a few days. It will take a few days and all these giants will just collapse. And this is one of our kind of struggles, that scientific software, I'm not talking about some web development, I'm talking about scientific software, like solving scientific problems, has been pushed primarily from academia, especially in the hard early stages, on the startup stages. Then it helped companies scale up extremely and make ridiculous amounts of profits. And these companies very rarely give back supporting the software. Actually, sometimes what they do, they try to buy out all the open source developers, get them in the company to work on some project that have no purpose. They're only profit focused. And this has created all sorts of issues. There are companies like Google with Google Summer of Code that has tried to help open source project by giving some money every year for students to learn how to develop open source projects. There are some bright stars in this. No, it's not everything is not dark in a way, but many of the companies have used to assume that it's going to be always some scientific open source software there. And the students have got used to it, and this is something now we have to deal. At the same time, the government is saying, well, if you want to get funding, you have to apply for grants, you have to ask for that funding. And also they tell you, oh, your project is now successful, why don't you make a company? Why don't you go and make...
monetize,
Yes, so what we're doing now, because we don't have other options, we are not only applying for grants, we have our own clients, we are opening our portfolio completely. Of course, it's a lot of work. It's very hard to do, but we're opening our portfolio completely. We are accepting clients. So a lot of open source projects in order to survive are doing that, which is a bit strange because usually when you have for example, you have a city, the city has roads. You don't go every day to just pay for these roads. In a sense, open source is the foundation to run technology and accelerate technology. Without open source, you cannot do it. Then if you remove open source, it will be again a company builds an operating system, but nobody can create applications for it because it's just too expensive. Things will just stop working.
Was thinking about more philosophical, and we're going like a modern age library of Alexandria or something like that, or like basic laws that we need to have access to right now to do. It's really, really interesting of how working together could actually get us in so many fields into getting to some extraordinary results. And actually, this is, if we pause over here talking about the products, I would love to have a bit of a conversation about managing a lab, which is a lab in a way of a physical way, but actually managing a lab that has probably employees and people all over the world. And